So I then move on to the next eigenvalue. That is for lambda 2 equals -1. I'm going to find the corresponding eigenvector. So you will recall, find the corresponding eigenvector for each of the eigenvalues just simply implies just solving this system here. So I'm going to solve that system for the next eigenvalue. So we'll say for lambda 2 equals -1 a minus lambda ix equals 0 is the same thing as, so our a, and we said lambda now is going to be replaced by -1 in the coefficient matrix, and then what we would observe, all we're going to have there is 1 6 0 1 1 1 and then 1 1 1 times my x, which is x, y and z, equals 0. So we said this 0 is a column vector here, 0 0 0. So we want to solve this. So like we said, to solve any system of equations like this, the very first thing you want to do is to row reduce the coefficient matrix. This is the coefficient matrix here. So when we row reduce, so maybe I should write that boldly. So you row reduce it. So when you row reduce this matrix here, what we obtain is you have 1 0 6 all over 5, then you have 0 1 -1 divided by 5, you have 0 0 0. So you observe that all the matrices that we've been reducing, after the reduction we always have a column that contains only zeros. Whenever you reduce to echelon form and then you do not have only zeros in one of the rows, then you must have made a mistake. So you should always use that as a check in trying to see if you're on track or you're wrong. As a check, let's check the first one we did. So you'd observe that when we reduced the coefficient matrix here, what we had was, we had this non-zero, but we still had a row that contains only zeros. So that's to remind you, if you're reducing to echelon form and then you observe that after the reduction one of the rows are not all zeros, then you are wrong. So you should go back and check or trace your mistakes. So this is x, y, z equals 0 0 0, and then when we expand this, this is 1 times x, which is x plus 6 all over 5z equals 0, and then we have y minus 1 all over 5z equals 0. So we want to solve this, and in trying to solve this, as usual, the very first thing is to recognize the free variable. The free variable here is z. So the free variable is z. So since the free variable is z, we set z to any number. Any number works, but I always like choosing z equals 1 because it's a very nice number. So when z equals 1, I can find y. My y is going to be, when we bring this here, becomes z all over 5, and since z is 1, this is going to be 1 all over 5. So my y equals 1 all over 5, and then similarly my x equals negative, when we bring this to this side, becomes negative 6 all over 5 z. So my x equals negative 6 all over 5 z. My z is 1, so that's negative 6 over 5. So with this, I've been able to find my k2. My k2 is minus 6 all over 5. My y is 1 all over 5, and then my z is 1. So this is what I have for my k2. But then this k2, which is an eigenvector, it's a solution of the homogeneous system. And then you recall the superposition principle that says that whenever any vector is a solution of a system, then the multiple of the same vector is also a solution. So I could rewrite my k2 to just be, since I have fractions here, I want them to all be whole numbers. So for them to be whole numbers, I'm going to multiply all of them by 5. So what I'm going to have is negative 6, negative 1. Let me multiply all through by 6, negative 1. So I'm multiplying this now. Let me write here. So multiplying by negative 5. I want my first number here to be positive. So note, you don't really have to do that, but my aim is I'm actually driving, I'm working towards getting what I've been told to prove. So I'm working towards doing this. So you can see that the first number here is just positive here. So that's my aim. So that's 6. And then negative 5 times 1 over 5, that's negative 1. And then we also have negative 5. So I've gotten the next eigenvector. So the next one I want to find is for lambda equals 3. So the eigenvector that corresponds to lambda equals 3, that's for lambda 3 equals 3, a minus lambda I x equals 0 is the same thing as, so a minus lambda I, wherever we see lambda, replace it with 3 in the coefficient matrix. So we have negative 3, we have 6, 0, 1, negative 3, 1, 1, 1, negative 3, times our x, which is x, y, z. Now equals 0, 0, 0. So similarly, we will reduce this to echelon form or to row canonical form. So when you row reduce that, what you have is 1, 0, negative 2, 0, 1, negative 1, 0, 0, 0. So, and then we have our x, y, z still back there, equals 0, 0, 0. So this is what we have. And then since we have done the row reduction, I could multiply this and then write them back in equation format. So that's 1 times x, we have x, 0 times y is 0, minus 2 times z is negative 2z equals 0. And then we have y minus z equals 0. So again, you would observe that the free variable is still z. So since the free variable is z, I'm going to start by setting, so I need a basis of this whole thing here, the basis of the eigenspace. So I'm going to start by setting my z to be, like I said, I like to choose 1. So if my z is 1, then my y is going to be, when we bring it here, you're going to have, it's going to be z, which is going to be 1. And then similarly my x is going to be 2z by bringing it here, and that's 2 times 1, which is 2. So my y is 1 and my x is 2. So having gotten that, now I've gotten my third eigenvector, which is my x, 2, 1, 1. So now I have my k3, which is 2, 1, 1, that corresponds to lambda equals 3. I have my k2, which is 6, negative 1, negative 5, the eigenvector that corresponds to lambda 2 equals negative 1. And then lastly, I have my eigenvector this, negative 3, 1, 1, that corresponds to lambda 1 equals negative 2. So I'm going to rewrite my solution here. This is going to be my general solution now. So therefore, the general solution is going to be x equals, as the general solution of the system which I'm trying to solve, is going to be x equals c1 k1 e to the power lambda 1t plus c2 k2 e to the power lambda 2t plus c3 k3 e to the power lambda 3t. And that's the same thing as c1. K1, according to what we got above, is negative 3, 1, 1. And we said this eigenvector corresponds to negative 2 plus c2 into 6, negative 1, and I think I got 5 there, negative 5. Yeah, but I'm very sure of that. E to the power negative t, then plus c3 into 2, 1, 1 into e to the power 3t. This is what we got. So let's check. We're told to prove that the general solution of the homogeneous system is actually this. So this is negative 3, 1, 1. Let's see. So you'd observe this is the negative 311 e to the power negative 2t, 211 e to the power 3t, and 6 negative 1 negative 5. So when we compare that and what we have here, you'd observe that we actually got the same thing. This is the general solution. So we have proved it. So it's proved. And that completes the proof.